Okay. Chapter 1. So last time we finished derive the equation for 4 reactors, right? Batch reactor, CSTR, PFR, and the PBR. So I hope you have memorized 4 characteristic equations for these 4 reactors. And we last time we finished example 1-1, right? So now please go to slide 23. The last section in chapter 1, it is just the introduction for industrial reactors. So normally I would not have any test in this section, but this section is useful. I think it is useful for you to select reactors in the future. So the first one is liquid phase reactors. The first type is semi-batch reactor. Semi-batch reactor. That means there is inflow but no outflow. For the batch reactor, as I introduced, the batch reactor is there is no inflow and no outflow, right? Because batch reactor is not a continuous reactor, so no inflow and no outflow, only a sterner here. But for the semi-batch means similar to batch, but a little, it is not exact batch reactor. Semi-batch reactor, there is inflow but no outflow. Okay, it is for the like a 2-phase reactor with bubble, gas bubble, the through liquid. So that means initially there is liquid in the reactor. During the reaction, there may be a tube. Inside the tube, there is gas, such as oxygen or nitrogen or hydrogen, for example. So maybe you are doing some reaction. Your reactant is like oxygen or nitrogen. So during the reaction, you continuously have an inflow of gas to react, but no outflow. That is the semi-batch reactor. Okay. So what is the advantage? Because there is a inflow, or you can call it feed. Okay, because there is a feed, so you can control the temperature of feed, right? If you want this tank to have high temperature, you can provide a feed with high temperature. So you can control the temperature by regulation of the feed rate, the first advantage. Okay, the second one, you can minimize the unwanted side reaction through maintaining low concentration of one of reactant. That means if you know some side reaction, the chemical reaction for some side reaction, and you know how to reduce the generation of side reaction by controlling some reactant. So you can just control the composition of feed to minimize the unwanted side reaction. So you can do more for the semi-batch reactor than batch reactor. Because for batch reactor, you can only put something and do the reaction, right? For the semi-batch reactor, you have inflow. You can do something for the inflow and control the temperature, control the reaction in the tank. Okay, but what's the disadvantage? The disadvantage for semi-batch reactor is the same as batch reactor. So you can see at the bottom 3 points. First one, high labor cost, because for every different batch, you need a different people. So high labor cost. Second one, the variability of products from batch to batch, because they are totally different reactors, so there may be some reaction on your product. The last one is difficulty of large-scale production. As I mentioned, the batch reactor is normally used in lab for small-scale operation, especially for some experiments. Okay, so let's see the second one. Slide 24. Continuous stern tank reactor, CSTR. You can see this picture. The tank is very similar to batch reactor, but they are continuous. So you can connect different CSTR in series. It can be itself, or it can be connected in series. The advantage for CSTR is good temperature control because it is well mixed. So if you see this, like this, sterner, if you see this one, it means it is well mixed. Okay? So for the well mixed solution, the temperature control is good. The disadvantage, the conversion is the smallest among flow reactor. Conversion is the smallest among flow reactor. Do you know what belong to flow reactor? CSTR, PFR, and PBR. Okay? Flow reactors. These 3 are flow reactors or continuous reactors. So among these three, CSTR has the smallest conversion. We will verify this. Smallest conversion in chapter 2, okay? Because CSTR has the smallest conversion, that means the size is the largest. You should use a larger tank to realize some conversion. Size is the largest comparing to these 3, okay? For the sort of flow reactors, CSTR, PFR, and PBR, CSTR has the smallest conversion, so it needs the largest size to realize your target. Okay, please go to 2025. Gas phase reactor, PFR. PFR is one long tube or several shorter tubes connect in series. So you can use one or combine several reactors. The advantage is easy to maintain because it is a tube-like reactor. So comparing to CSTR, this one has the highest conversion. So please remember, regarding to conversion, CSTR has the smallest conversion, but PFR has the highest conversion. Highest conversion. So that means the size is not required to be very large or very long. It is the advantage of PFR. How about the disadvantage? Actually, you can just compare CSTR and the PFR. The advantage of CSTR should be disadvantage for PFR. Okay, they are different type. So the disadvantage for PFR, the first one, difficult to control temperature. This one is different from CSTR, right? The advantage for CSTR, you can see in slide 24, easy to maintain good temperature control for CSTR. But for PFR, you know, PFR is like a tube. It's like a very long tube. So you cannot control the temperature like at the very deep side of the tube. It is hard to control comparing to this kind of tank. So the disadvantage for PFR, difficult to control temperature. And the second one, because the temperature is hard to control, so hot spots will occur when the reaction is exothermic, especially at the deep side of reactor. Some hot spot will damage your reactor. Okay, let's see. So 26, I have some important conclusion for comparing CSTR and the tubular reactor. 26, okay. The first sentence, the very different part is the liquid phase and the gas phase. I have mentioned, right? For CSTR, it is a liquid phase reactor. For PFR, it is gas phase reactor. Or you can see for tubular reactor. And for both of them, homogeneous. So which one is heterogeneous? PBR, right? PBR is heterogeneous. Or PBR dealing with the heterogeneous reaction, like the solid and the liquid, solid and the gas. The solid is catalyst. Liquid or gas is your reactant. So for the PBR, it is mainly for catalytic reaction. So they contain solid catalyst for heterogeneous reaction. Okay, so PBR is in 27. Okay, PBR is also a tubular type reactor, but it is packed with solid catalyst particle. As I mentioned, heterogeneous reaction system in PBR. Okay, but the configuration for PBR is very similar to PFR. They are tube. They are both tube type. So the advantage, first one, highest conversion. PBR is similar to PFR. So the same sort, right? The tubular type, highest conversion. Smallest conversion for CSTR. So what's the disadvantage? I think it is very similar to PFR. So the first disadvantage, difficult to control temperature, like PFR. Second one is only for PBR. Catalyst is usually hard to replace. So you can see, you can image that there is a very long tube. So how to completely replace this catalyst? It is hard to replace a catalyst in the tubular reactor. And the last one, channeling of the gas flow occur. Channeling of gas flow 是气路堵塞 就是管子很长，有一些气体会堵塞在里面。Okay, so channeling of gas flow will result in ineffective use of reactor bed. Part more, 28. This one is fluidized bed. It is very similar to CSTR, but it is in heterogeneous system. So it is like a heterogeneous type CSTR. This one is the configuration of tank is just like CSTR, but there are several solid catalysts packed inside. So you can see the advantage is similar to CSTR because the configuration is CSTR. First one, well mixed, good temperature control, and it can handle large amounts of feed. The last one is very different from PBR, right? The last one, easy of catalyst replacement. I just mentioned for PBR, this kind of tubular reactor. You can image a very long tube. The catalyst is hard to replace, but if you use this kind of tank, like CSTR, the catalyst is easy to replace. So among these reactors, you can compare the similar part and the different part to memorize everyone. You can first list the similar part, and you can tell the different part. Otherwise, you will get confused. So please go to the last one, 29. It is like a review, summary. Okay, 29, last one. The summary of chapter 1. There is a table, right? The table shows the reactor more balance. So the first column show you 4 reactors, batch, CSTR, PFR, and the PBR, and their illustration are shown at the left-hand side. So you can find the batch reactor and the CSTR are very similar. The different part is CSTR has inflow and outflow, right? For batch and the CSTR, the configuration are the same, but CSTR has inflow and outflow. PBR and PFR tube, but PFR, there is no solid catalyst. For PBR, there are several solid catalysts. So you can use this table to review the chapter 1. Okay. The second column shows you the special part for each reactor. The batch and the CSTR, the first one is no spatial variations. 没有空间上的差异。No spatial variations. It is result from this one, the 搅拌。当你有搅拌，它就没有空间上的差异。The sternum means no spatial variations for batch and the CSTR. Okay. As for the flow reactor, CSTR, PFR, PBR, they are in steady state, right? Steady state. So if you remember, steady state means something dt is equal to 0. Nothing changes with time. So every turn dt is equal to 0. The third column shows you the more balanced differential form. You can find the CSTR has no differential form, okay? Because for CSTR, the differential term is deleted. CSTR differential term is deleted. So you can only see the normal form for the CSTR, okay? So batch, PFR, and the PBR, you have differential form and the integral form. Other than this table, you have to memorize the equation, characteristic equation I just derived. Like in, let me see. We have quiz next week, okay? And I think I must have some problem for you to derive the equation. 有些公式推导你要会哈 ，so please memorize the general more balanced equation and some characters for the tank, for the reactor, and you can do some simplification, derive the equation. Maybe for the batch reactor, slide 10, you have the characteristic equation for batch at slide 10, right? And then for the equation of CSTR, that is in slide 13. The equation for PFR is in slide 15. Last, the equation for PBR is at slide 17. Okay, so please know how to derive this equation. And also there's only one example here, so you must know how to solve this problem. Okay, please, let's continue to chapter 2. We are still want to dealing with the reactors. So batch reactor, CSTR, PFR, and no PBR, okay? Mainly CSTR and the PFR in chapter 2. CSTR and the PFR are mainly discussed in chapter 2. So let's see the topic of chapter 2, conversion and reactor sizing, 转化率. So conversion is very important when you decide a reactor. There should be a target, right? There should be a target. Maybe I want the over than 80% conversion. Then how large reactor should I have? Should I design? So the conversion is very important as a parameter to decide the reactor. And the second part is reactor sizing. Sizing 设计个反应器的大小. So the next slide, there are 4 targets to learn in chapter 2. First one, evaluate general more balanced equation to size CSTR and PFR. So you have to use the equation to decide what's the size, how large for the CSTR and the PFR. The second one, define the conversion. And you use conversion X. You use X to rewrite more balanced equation in terms of conversion. So in chapter 1, there are 4 different equations from more balanced equation, but there is no conversion X. In chapter 2, the equations are similar, but X conversion will be put in the equation. Then you can use those equations to calculate the conversion directly. Okay? The third one, sizing a reactor with the relationship between reaction rate minus RA and the conversion. Minus RA, we just mentioned at the beginning of chapter 1. Last one, compare CSTR and the PFR and the overall conversion for reactors arranged in series. So the last part, there is not only one reactor. I mentioned you can use one reactor or you can use several reactors connect in series, right? 你看可以单独的或是把它串联. The last part will talk about the reactor arranged in series and how to calculate the conversion in this kind of system. Okay, so let's go to the first one, definition of conversion. Slide 3. let's consider general reaction. AABB become CC and DD. Okay, so normally we will control the one species with the coefficient 1. So it could be like this. And normally A is limiting reactant, 限量试剂. Normally, so you can do it or not. Limiting reactant. Normally. So normally the coefficient for limiting reactant is 1. That will be easier for you to do the following calculation or following analysis. So when you do this, every quantity is on the basis. The basis is on per mole of A, right? Because the coefficient of A is 1. So in this reaction, in this chemical reaction, every quantity is based on per mole of A, and it should be suggest you to have a limiting reactant as A. Okay, so the first modification. So let's talk about conversion. Okay, in slide 4, conversion X. Conversion is X, and you can put a target here. So it is the conversion of A. Okay, conversion of A means number of moles of A reacted per mole of A feed to the system. So SA is defined as moles of A reacted over moles of A feed. It is the definition. How much A you put in the reaction, then how much A reacted, that is the conversion. In two reactions for the irreversible or in the reversible reaction, okay, for the irreversible reaction means the reaction only go one way, right? Go one way. So the reactant is continuously consumed. Nothing back, right? Only this way. Irreversible reactor. So the irreversible reactor, the maximum conversion is equal to 100% or 1, right? For the irreversible, reaction, irreversible reaction or reversible reaction. For irreversible reaction, maximum conversion is equal to 100%, or you can say X is equal to 1. The same, right? 1 and 100%. For reversible reaction, reactant product, they will go back and forth several times. So the maximum conversion for the reversible reaction, X is equal to the equilibrium conversion. XE means equilibrium conversion. There should be a balance, right, at the equilibrium type. Finally, it could be at equilibrium. So if one problem asking you about maxima conversion, you can just tell it is irreversible or reversible. If the reaction is irreversible, you can just give me the answer 1. For the irreversible reaction, maxima conversion is 1, maxima. All the reactants are reacted 1. But for reversible reaction, you should do some calculation to find the balance, to find the equilibrium conversion. So now I want to put a conversion in more balanced equation. Okay. First, for the batch reactor, slide 5, batch reactor. We'll talk about batch a little bit. First, for batch, the purpose is to put the X conversion, to put a conversion into the reaction, into the equation. So slide 5. The conversion increases with time spent in the reactor. For batch reactor, if you remember, the characteristic equation is for time, right? For batch, T is equal to something. So time is important for batch reactor. The longer for the reaction, higher conversion you will get. Okay? So for batch reactor, moles of A reacted is equal to moles of A fed times this one, moles of A fed and moles of A reacted. This equation is a normal equation. Hello. This equation is a normal equation because you can find this one is the same as this one, right? This one is the same as this one. So just a mass. But we can put a different symbol to represent. Moles of A reacted is equal to, what is moles of A fed? It is Na0. Okay. Mole, the symbol for mole is N. Remember, right? Mole is N. Your target is A. Initially, fed is initially 0. So Na0 is the moles of A fed. What is this term? This term is a conversion of A. Okay, so moles of A reacted is equal to Na0 times Xa. Or you can just write X. It is okay. But Xa is more specific. Okay, that is slide 5. So now we have the moles of A reacted, right? At slide 6, the number of moles of A remaining in the reactor after time T, how to write down this one? after time t, what is the moles of A? Moles of A in reactor at time t. Okay, it is equal to moles of A initially fed to reactor. Or you can say it is time equal to 0, right? Initially, minus reacted, right? Minus moles of A consumed by chemical reaction. So that is the full description, how to have a symbol form. Moles of A in reactor at a time t is Na, okay, Na. Any time t, the moles of A in reactor, Na. The moles of A fed is Na0, right? And how's this one? Moles of A consumed or moles of A reacted. Na0 times X, right? And also you can write down like this. So please remember this relation. Na is equal to Na0 times 1 minus X. We use this relation to put the X in characteristic equation. Okay, so remember Na is equal to Na0 minus Na0x. So before class dismiss, I want to show you how to put a conversion in the equation. So it's slide 7. Okay, slide 7. First, please put a more balanced equation for batch reactor. Okay, I directly take the equation from chapter 1. Okay, from chapter 1. We have this conclusion, right? In chapter 1, we have this one. You can check if you forget. Check in your handout in chapter 1. So, beginning by using this equation. Second one, let's have an equation of conversion. Okay, so you know Na is equal to Na0 minus Na0x, right? As shown there. So you bring this one into this one. Okay, so you differentiate by t. Differentiate by t. Differentiate the equation by t. You can obtain for each one dt. Okay. So this one, the Na dt. This one is a constant, right? Constant dt is equal to 0. And this one is constant, so bring it outside. We only have the x dt. Okay, so let's bring this one into the more balanced equation. So the second one, bring the second one into the first one, okay? The equation in second one into the first one. So replace this part, right? Replace this part you have. Okay? Or you can put it like this. As I mentioned, RA is less comma. Minus RA is comma, right? So this one is better. Minus RA is better. So this is the design equation. Of batch reactor in terms of X. So we successfully put a conversion into the equation. What's more? Then, how to determine time to achieve X. Assume V is constant, okay? If V is a constant, what is the time to achieve X? So starting from here, from the equation in the third point, you have this one. Then do some calculation. Okay, please do it by yourself. Do some calculation, you can get okay. It's just a calculation for the integral. So oftenly, time is important for batch reactor, and the conversion is important to achieve. 这字写错哈。Okay. Any question? Okay.